Moving on to Chapter 7. Chapter 7 is about random variables. Now, the notion of a random variable extends what we were talking about in the previous chapter in a special way. So, in the last chapter we were talking about random experiments. Remember that a random experiment was just some well-defined procedure where we didn't know what would happen. So it had an uncertain outcome. Now, what random variables do to extend this notion of a random experiment is that we're now going to assign numbers to various events or outcomes from a random experiment. So certain outcomes will get mapped to a certain number, and then we will do things with that number. So here's the way Chapter 7 is going to work. We're going to talk about random variables in general, and then slightly more specifically, we're going to talk about discrete random variables. So discrete random variables, the discrete random variables that we'll talk about will only take a handful of possible values. Then we're going to move on and talk about two special random variables. We'll talk about the binomial random variable and the normal random variable. So let's go back to this definition. So random variables assign numbers to outcomes from a random experiment. Let's go over to the sketch pad for a second, and I'll give you a specific example of this. So let's say I have a random experiment where I take out two coins from my pocket, and I happen to have a penny and I also have a dime in my pocket at this point. And I shake these two coins up, I mix them up very well, and I throw them into the air, and then they land on the ground, and I observe what happens. Now let's think about what could happen. There are four possible outcomes. One is that the penny comes up heads, and the dime also comes up heads. Another is that the penny comes up a head, and the dime comes up a tail. We could also have a tail with a head, or we could have two tails. And I claim that these are the only four possible things that could happen. So what I've just described to you is right out of Chapter 6. Now let's make this into a Chapter 7 problem. And I'm going to add a column to this table, and I'm going to say let x equal the number of tails. That's a T there. So what we've just done is to take outcomes from a random experiment. So here are the outcomes from a random experiment, and we're going to map these outcomes to numbers. So in this case, the number is 0. Here is 1. This outcome also gets mapped to a value of 1, while this value gets mapped to a value 2. So this piece right here is the Chapter 7 piece. So that's what a random variable is all about. Now what we're going to be doing is kind of a repeat of what we did in Chapters 3 through 5. We're going to be looking at things like how often do each of these values occur. We're going to say, could you give us a frequency distribution of this? But instead of calling it a frequency distribution, we'll call it a probability distribution. Another thing that we'll do is we'll ask things like, what's a typical value of this distribution, and how dispersed are the values of this distribution? So let's go back to the course packet, and we'll go to the next slide. Consider another example of a random variable. Suppose that I ask somebody, how likely are you to buy this product? So I expose them to a product, and I say, rate on a 5-point scale your intentions to buy this product. So purchase intent. Now, back in Chapter 3, what we would have done is formed relative frequency estimates of such a random variable. We would have gone and asked, say, 100 people, how likely are you to buy this product? We'd observe, are they highly likely or just somewhat likely of 4, and so forth. And then we would tally up the results, and we would make a frequency distribution. All right, so we'd start with the data and come to a frequency distribution summarizing it. Well, in Chapter 7, what we're going to do is start with the distribution and then talk about that. So this distribution is what would give rise to such data. So we're going to just assume that, the chance that somebody says 5 is 25%, chance that somebody says 4 is 0.4, 40%, and 1s are very unlikely. So notice these values all sum to 1, so we have a sample space here. So that's the entire sample space. We've mapped the entire sample space to these numbers 1, 2, 3, 4, and 5. Now, there's a lot of parallels between what we're doing now in chapters 3 through 5. What did we do next after we had a frequency distribution in chapter 3? Well, we graphed it in the form of a histogram. Here is a graph of, we're going to call it a probability mass function. Here's the graph of it. So notice the heights and areas of these bars correspond to the values in this frequency distribution. One more piece of notation for you. So we will use this notation. So the probability, the way I will pronounce this is the probability that x equals 1 is 0.05. So we will write this, the probability with a random variable equaling something or greater than something, all within the parentheses, and then we'll give that a value. Well, you've just had a rerun of chapter 3 in the context of a probability theory where we start with the distribution. Let's move on to chapter 4. So chapter 4, remember, said, tell me about a typical value of this distribution. Well, we had 3 measures of typicalness, means, medians, and modes back then, along with various hybrids like the trim mean and so forth. For this chapter, what we really care about is just the mean. So we have a slightly different set of names and symbols for the mean, but they're just means. So the population mean, which will also be called the expectation, is this, mu. So mu is the symbol used back in chapter 4 for the population mean. Nothing really different there. We're often going to write mu sub x just to emphasize that this is the mean of x, it's not the mean of something else. Very soon we're going to be talking about multiple means within the same problem, and so keeping track that this is the mean of x will help us. Another symbol that we're going to be using is e at x. So this is the exact same thing as mu. So this is pronounced the expectation of x. And again, this relates back to typicalness. So what's a typical value, or what do you expect? What do you expect the value to be? These are all synonyms for the mean. Now we have a formula that you've seen before. This is the formula for a weighted mean. What we're going to do is weight the values by the probabilities. So values that have higher probabilities and are therefore more likely to occur get more weight than those that are less likely to occur. So let's just go find the mean of purchase intent in that previous scale. What I'm doing is I'm implementing this formula. So we're going to take probability of x times x. So 1 occurs with probability 0.05, 2 occurs with probability 0.1, and so forth. 5 occurs with probability 0.25. If we compute this sum, we get 3.7. So 3.7 is the mean of this distribution. Now the same rules apply. If I were to stick a wedge at 3.7, so the arrow of my cursor is a wedge, think of it, this thing would be in balance at the value 3.7. One other thing to note about this mean, I called it a weighted mean. The reason is we're going to give a whole lot more weight to values like 4 and 5 than we are to values of 1. Let's contrast this with an unweighted mean. So let's go over to the sketch pad for a second. And down here, let's just take the value. Let's say I had observed the values 1, 2, 3, 4, and 5. And I wanted to find the mean of those numbers. What would I do? Well, I would say 1 plus 2 plus 3, plus 4, plus 5, and what would I do? I'd divide by 5. All right, so you can think of this as 1/5 times 1 plus 1/5 times 2 plus 1/5 times 3, 1/5 times 4, and 1/5 times 5. Now, what I've done, what I was doing back in chapter 4 was assigning equal weights to every number that I've observed. So we were saying, well, 1s are just as likely to occur as 5s, therefore each number gets the weight 1 over n, or 1/5. What we're doing here is quite different. We're saying these values are more likely to occur, so therefore they get bigger weights than 0.2, which would be 1/5. This number 1 is very unlikely to occur, therefore it gets less weight. So that's what I mean by a weighted mean. Let's now go on to chapter 5. So in chapter 5, what did we do? We asked questions like, how dispersed is this variable? Well, we can do the same thing with a random variable, and here's the formula. So remember what variance was. Variance was the typical squared deviation from the mean. So if we go back and scribble that formula, the typical squared deviation from the mean was 1 over n times the sum of xi minus mu, squared. So this piece was the squared deviation from the mean. Each one of those squared deviations had a common weight, which was 1 over n. Well, what are we going to do here? Instead of giving them a common weight, we're going to let some of them have more weight than others. So the values of x that are more likely to occur get more weight. So let me write out this formula for the problem that we just discussed, the purchase intent problem. Well, let's think about how far is 5 from the mean. Well, there's the squared deviation. We give that weight 0.25. 4, okay, is also extremely likely to occur, so it gets weight 0.4. While the value 1 is not very likely to occur, so the squared deviation from the mean, 1 from the mean, is only gets weight 0.05. So if we compute this out, we get a variance of 1.21. Then we can find the standard deviation by taking the square root, which is 1.1. Now, students often make mistakes when they use these formulas. So I've tried to come up with a foolproof way of finding means and variances, and here it is. So I call this Ed's table, and I strongly recommend that you get good with my table. Here's what you have to do. First column, you put in all the values of the random variables. Second column, you put in the probabilities. Third column, you multiply across. So 1 times 0.05 is 0.05, 2 times 0.1 is 0.2, and so forth. Now if you add these up, you will get the mean. So just multiply across, add up, you get the mean, and so you see 3.7 is exactly what we found going directly to the formula. The variance is going to be similar. So we're going to find the squared deviation from the mean and then weight it by the probability. So we find those numbers, add them up, and you get the variance. So that's about it for these little discrete random variables. You should now be doing the first 8 problems or so in Siegel, and make sure you watch the videos for some of these problems. Okay,